last week we only had Monday, Tuesday. I think it was 2 weeks ago, actually, that we talked about this. We are having a water balloon launch contest. Right? So, we previously, when we talk about speed, have a pretty easy job at doing so. Because we're normally talking about miles per hour, and often you can just look down at the little thing in the car and, ask, how fast are we going? The problem is, what if I ask you to answer that question at a specific moment? Like, how fast is this ball going? Let's declare something right now relative to the Earth. So, of course, if we get real literal, this ball is moving extremely fast through space. But relative to the Earth, it currently is not moving, right? So we'll agree that, like, things that are moving with the Earth, we're going to say have no speed. But, like, how fast is this ball moving right now? 0, right? So we can agree on that. Then, how fast is the ball moving when I clap my hands? Versus different time, right? It was on the up. Now wait, what about
when you clapped, it was at the vertex and it wasn't really moving?
Ooh, there is a point where it stops. This table needs to be heavier because I lean on it and it slides and it is awkward. Then it's off angle and it bothers me. So this is what we call projectile motion. So if you would like to write down that fancy word on your paper, that would be great. Projectile motion is an object that's moving. Oh man, what a hard definition. Wow. Now, when we get more complex about projectile motion is an object that's moving that we can talk about the speed of at any one given moment, but that speed may not be consistent throughout the travel of the object. So obviously, it's fastest when it leaves my hand, stops for a moment, and it keeps doing that over and over and over and over. Yeah, when that bounced its way over to nothing, there were a bunch of moments where it didn't have any motion, quote unquote, when it paused right at the very top, and then started again. So it's got movement up, slowing down, stops, has movement going down, speeding up, hits the bottom, for a moment probably stops, rebounds, comes up, at the fastest it will be traveling, slowing down till the top, and this happens over and over and over again. We are going to look at how do we determine the speed at any given moment. So, Sasha gets a high-speed camera, and she uses video footage, which that's not really a correct, well, maybe it's a correct word. Anytime people talk about like film and things like that, I like to snicker and say that doesn't exist anymore because nobody uses film these days. You can. You could still go to the store and buy film. But, so, she uses an app to record the approximate heights at specific times of Maggie's water balloon, data shown there. So we can obviously, going up, around 2.5 seconds, it makes some kind of turnaround, but that's not the vertex, because we can see that it doesn't mirror the activity.
Should we graph this?
That is, oh no, that's Jen's that you have on your paper. So we have Maggie's balloon here, right? They tell us, oh wait, here we go. They tell us the max height is 90.75 feet. 30.25 yards. I don't know why we're working in feet and yards. Come on, be scientific. How quickly did her balloon rise and fall? That is, what was the balloon's velocity during different times of its flight? So let's just pick a few different points to kind of talk about what is the velocity. So let's go ahead and graph this data, and you can use the graph that you have if it. So does your graph go up to 90.75? Sure. Does it go up to about 5 seconds?
Yeah.
Sure. So if you want, you can go ahead and throw these points on your graph real quick, knowing that your vertex is like right about here in between 2.5 and 3. Okay, we just need to make a plan. That would be the thing. Like, I'm totally down with it. And I will tell game people there's no games today because it's 65 degrees outside. We're talking about being able to take 7th grade outside for lunch. that's not up to us. I don't eat 8th grade lunch. I go home to dogs then.
It's nice. Outside it is.
Dog. Wait a minute, this looks
It
a
is not
lot.
feasible. I tried it last
Are your
Wednesday.
points almost exactly on check?
It's not feasible to go at the Rockbridge
No.
store.
Oh,
Like,
yeah.
well,
It's way
yeah.
too much
Well,
of a
and then
distraction, and then you
that
gotta
walk
walk on
out
that bus that
front,
way, which
yeah, it's
I mean
just
there really
dangerous.
shouldn't be any traffic going that way, but so I think that really the only logical
You should
thing
walk
is
down, go out the office.
it's gotta
I mean, it's the safest. It's the easiest to keep track of who's coming in and out.
and then trash cans can be placed right
Or
by
we can
there
use the
or
outside trash cans if we tell custodial that they'll be taken out more frequently.
that's true. Although I think
It
Worthington
might be
Parks
a
and
pain in the
Rec
butt, though.
is the one in charge of them too.
Oh, well,
Which
yeah. I mean, we may just need to figure out a solution to that. But like, a kid would need to bring a trash can down, and I honestly, well, I don't know. I was thinking about you just have to carry all your trash back over to like the trash cans by the door, but I know we'll have trash along the way. So then we're gonna answer the questions of what is your rate of change? What's your speed between half a second and 1 second? Is going to be your first moment that we look at. What is the speed? I love projectile motion. Things that are constantly changing. Like, you can't really answer the question of how fast is this going, but in a snapshot moment, you can make an approximation. I need to send you another podcast. And actually, you guys will be interested in this too. I need to use Schoology more. Actually, my doctor would advise that because they said one of the things I just need to do is just walk. They said, after just walk as much as possible. So this one is in the TED Radio Hour.
Okay.
And it is literally called Solve for X. So it's an episode all about math. But they start in the pretty close to the beginning. They talk about the why is X X. And I'd never actually known. Like, I never knew the real, like, why did we choose X versus any other letter? And there's a legitimate reason why we use X. And it goes back to the Greek letter chi, which goes back to the fact that you can't make a sh sound in Spanish. And the word that, I want to say Indian mathematicians, or I'm probably getting it wrong, were using for the unknown quantity was like Sheyan or Sheon, some word that like when you went to translate it over, you needed the sh sound, and there wasn't a sh sound. So instead they used the k sound from chi, so they replaced the sh with a k, and that's where X came from. Because literally X is that k sound in this word that they were using to, it literally means something.
Oh, something.
Yeah, the word like she.
Something multiplied by 8.
Yeah.
Huh. That's cool.
If we end up with time this year, guys, I will play you clips from these podcasts and stuff, but like, I spend my weekends when I'm doing stuff just trying to get smarter and listen to podcasts and learn things.
There was one on Through Line about the first like openly non-gender.
Hey, then try to answer these questions. I know we're going a little slow, but you actually have a lot of tasks to try to accomplish. And I would like to pull back and see if you're able to do it without me.
The latest reply all was interesting too.
Which
Stuck in his head.
Oh my gosh, dude! I swear to you, I am crazy. Because I was listening to that episode going like, I'm pretty sure I know this song. And I was probably just remembering the Bare Naked Ladies type of music back then. But yeah, the resolution to that was so unexpected.
Yeah.
Of just out of nowhere.
I was thinking that he created the song in his head and like more or less dreamed a song is where I thought it was going.
But that dude in whatever other country that also but then they started poking holes in that of like, well, okay, he had like 2 lines of lyrics. That was it.
2 points.
Can we go back to the actual thing so I can get the exact standpoint? Because
I can actually slide this up if I ungroup. There we go. need it up further, or are you good?
Yeah.
I'm gonna shrink this a little bit. Ooh. Yep, and then 1.75. When did it reach its maximum height? What was its speed? We already kind of talked about this because, again, I overteach. I like to give these intros where we have this conversation that in this class, they already figure out most of what we're trying to figure out today. Like, your velocity slows down, stops, speeds back up, and then does it all over again. And some of this is like they've done the bouncing ball lab in science in 7th grade, which I know they've done. So when we come to projectile motion, you guys have some of that set up. You did the golf ball lab, right, last year? For the height of the golf ball when it bounces. So you took a meter stick and you, how high, like you would measure. Like somebody tried to like, you didn't do that last year?
Yeah, we did. No,
Yeah.
I think we might have.
I think you did. I think some of you just aren't remembering.
Okay.
I don't know. It might not have been there. It might not have been there.
Wait, choose 2 points in the PE for the calculator.
Or was it card?
Wait, what? Choose 2
When you're trying to be fancy.
Well, I can do that with a soccer ball.
I can do
This
it
is
with a
just,
soccer ball too. It's just hard to do with something smaller. You're gonna hit.
it is.
Oh,
Trash.
It says just pick 2 toys from the table using the calculator.
Yeah.
So,
Couldn't
if
do
you're going to
1.5
try to
and
choose
2
approximate points, what points would you choose for C?
So see, you do 1.5 and 2, the
Yeah.
closest ones.
1.5 and 2 are the closest points that we actually have. So, let's go ahead and jump back together because I feel like I've waited way too long.
And couldn't you like find the slope and get like an approximate from
Yeah.
where it
That's
is?
what I was thinking. I was like,
So, what is the change in height there? 10.
Yeah.
Right? So, our change in height there is 10 feet.
So we
Change in time, half a second.
So we'd assume if it's plus a quarter of a second, it'd be like what close? About maybe.
What do you mean plus a quarter? Like, we are in that moment
Okay, so
saying from here to
Okay.
here. So, here, give me eyes real quick. From here to here, 1.5 in 2 seconds, we went from 78 to 88. We want the speed right here, but literally in a moment, there's no speed. If we just look at a moment, it's the ball wherever it is. We have to look at 2 moments to be able to calculate a speed. The data that we have, these are the closest moments. Now, if we graph it, like using a graphing utility, we might be able to get closer moments, like 1.7 and 1.8, right? Wouldn't 1.7 and 1.8 be better? Yes. But for what we have 10 feet in half a second, so the speed is 20 feet per second.
yeah, so per 1/4 of a second, wouldn't that be 5?
Yeah, but we don't talk like that. You want the denominator to be a 1. So like when we talk about miles per hour, feet per minute, like, math problems per whatever, like you normally want to talk about the denominator in 1. So in this moment, we're traveling at about 20 feet per second. Does that make sense to us? If we back up to the beginning of this,
Oh.
what's our approximate height right at the launch? About 68 feet per second, right? So I've gone from 68 feet per second to about 20 feet per second to what if I look right here between 2 and 2.5?
Well, it makes sense, right? It has to slow down to reach super.
Yeah, it has to slow down to, well, not it has to slow down, but it will slow down because gravity. Right now, if I throw something downward,
Then it has like the extra.
it's going to speed up. So when you start doing physics problems where you're up in a plane and jump out of the plane, you will speed up until, no, and this is interesting. Will a penny off the Empire State Building kill you when it hits you on the ground?
No.
Yes.
By physics, yes. It will. By physics, the penny will speed up to the point that it just goes straight through your skull.
Okay, so are you saying that, like,
Now, hold on.
in theory, with
Why?
physics,
In
a
theory.
child just happens to have, like, what if it was a
Dude,
quarter?
people do this. People throw coins off the Empire State Building because there's an observation deck. Did you guys go to New York last year?
Yeah.
Did you guys go up to the Empire State Building?
No.
So if you go to New York and if you go up to the observation deck of Empire State, there's a fence, but you could like like flick a penny through the fence. Now there are security guards. I got in trouble by the security guard. Because I was standing on a thing trying to take a picture of people, and he goes, "Sir, you can't stand on that. Sir, you cannot stand on." He was intense. Seriously, he like repeated himself before I could even process the words he had said. Don't stand on the railing on top of the.
Theory, a child is accidentally drops a penny not in the fence area, and just like. Oh,
But why
other person's just standing
doesn't
there at the bottom.
it?
Nope.
Why doesn't it actually kill anyone?
Because it can't actually speed up to that point.
Why?
Is it rotates?
Air
Well, they
resistance.
also have a that's what I was gonna say.
Air resistance ends up causing friction. Really, air resistance is friction, which makes the object reach. Anyone know what we call it? The fastest fast that you can get? Blank velocity.
Maximum.
Well, yeah, pretty much terminal. We call the maximum velocity that you can reach realistically terminal velocity. Now, in certain situations, we ignore those other parameters until the end, and then we'll redo calculations with air resistance and whatever else. Because honest to God, humidity plays a fact. Air pressure plays a
What
fact.
would
Like,
actually happen?
Wind.
if there was no air resistance,
So
and
if it was
if
like a
a
vacuum.
penny was just a ball of copper or whatever that was that mass that could fall ever increasing in speed, by the time it would reach the ground, we did this calculation in high school, it would have enough energy to puncture the human skull. Now the reason it can't is its mass is flat, has a bunch of surface area, and has a bunch of wind resistance. Even if it fell straight, like stood up, still too much wind resistance of the air coming around the penny, and it flips. Yeah, it can't fall. It just falls kind of fast.
Except hits a head.
It would just
Like it reaches terminal velocity pretty quickly, actually. Like
Wait.
within the first few floors of it falling,
Does
like
each
the first.
object have its own terminal?
Yeah, because how
okay.
much wind resistance does it have? Yeah. So a like lead cone, if you drop it point down, that is like on the outside covered in titanium, because titanium has very little wind resistance, would fall very, 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 very fast. As opposed to like a rubber, think about rubber as like friction and wind resistance, like that'll reach terminal velocity quicker because it has more wind resistance.
Also the wind.
All of that to say, we're ignoring those things here. Okay, we're ignoring those things here. What happened to the balloon just before and just after it reached its maximum height? Well, it has a velocity of next to nothing, right? If we get down to the moment of reaching the top and we shrink our time into like narrow enough, it has zero velocity. It literally for a moment stops moving and then comes back down. Which, if you've ever ridden like rides at the fair or whatever, that's that your stomach like coming up out of like that's that feeling where literally the inside of your body is still like I'm going up, and the rest of your body's like no we're not, and like that's what makes you feel like. And even on like elevators, you get a little bit of that where you're anticipating we're gonna keep going up at the same speed we were, but you don't.
And you just go,
That's why you feel like that.
and it's just like,
We can probably move on. All right. So Sasha has graphed Jen's launch, and you have it on your paper here. So based off the points we can find on there, I want you all to estimate what the speed is at these different times. And no, I will not answer questions about what points should we use or how accurate should we get. I just want you to take a couple minutes using the data on your paper, or like the graph on your paper. Now, if you want to really go above and beyond, and just because I know one of you is probably at least thinking this, yes, we could probably derive the equation for this parabola. You don't need, calm it down. You don't need to, but you could. Pouty Pollies. I just have to make up alliterations.
Oh, that was made up.
Like
Okay.
Sad Susan. Or like, come on, Karen.
I need to speak with your manager.
Did you guys see
Unless it's
the
Kim.
video that's kind of gone viral with that health official
Oh,
talking
and
about how we need to not touch our face,
Yeah.
and then she licks her finger
Yeah.
to flip the page?
that was.
Sorry.
It was like.
It was so funny. My wife works in the health department.
It was so funny.
These aren't. This is not the same data. This is a different launch. So we're not using the table. We're using the graph. So you have to derive the points. So if like t equals 2 seconds, you're gonna find 2 seconds down here and get as close as possible up here, and then make a little window for what values you want to use. I'm gonna pull up I have another copy of this that I can zoom in on easier.
Is it like 92 or 90?
We'll talk with each other.
I was
I'm
thinking
not
about
answering your
93
questions.
since it's about in the center of it. Because
93.
Well, we know it's in the 90s.
we know it's in between 90 and 95, and I'm
So
guessing
93.
93 since it's like about in the center.
93, let's say 91.
Man, I really wish that they had put this into Desmos.
Yes. No, it's like 92.5.
This is not in Desmos yet, but we should put it in Desmos. That would be great because then we could zoom really well. So you guys have 2 seconds.
Yeah.
You come up here,
I
you're
have,
at 90 something.
Yes, for all of them,
What's that 3?
David, why are you sitting there like a bump on a log?
What?
Do something.
What happened at 93?
At 0.5 seconds.
At 2.5? Wait, at 2.5 seconds, it's already past like the vertex, right?
It's about 35.
It said what? Okay. 0.1. Another point that we have is 0.535.
Yeah.
Oh, I thought we were just trying to find the one that it has, like TF2, TF 2.5.
One is about.
Well, so yeah, it has 2, 2.54, and 0.1.
Yeah, I was wondering why you're saying 0.5 because I got 0.1.
Point
It
one.
wasn't, but
Yeah, like a tenth of a second.
Is the speed of the thing always changing? Like at
Arguably, yes.
Very.
little changes, but like it's changing.
It's not like doubling its speed.
So let me ask a question back to you. Is the slope of a parabola ever the same?
yes, when it's because it reflects itself, so wouldn't it be the same on each?
Well, but those are inverses, right?
Yeah.
So
oh
not
wait,
really
so it'd be
the
like
same.
Because it's
It's cool when it works, but
What did you
when I miss, I just miss.
when you miss, you just go like.
Well, when it works,
When I miss, I just miss.
is that.
Yeah, you just like.
All right.
Hit the
So
ground and
from here, the slope to here is not the same, right? Is not the same there, is not the same there. So to talk about the speed, is it ever the same? No. Now one might be the same speed but downward instead of upward. Sure, if we draw this line, there should be like this speed here and this speed here should be inverses of each other, hypothetically. But yeah, there is no like same speed because the slope keeps changing. So at 2, what points can we use here? Well, we could just use this point because it's an intersection, and that point because it's an intersection. And I know I'm using the 2 seconds point, but I mean I can, right? That's going to be the speed up to 2 seconds, as opposed to the speed after 2 seconds. And of course, the smaller window is the better. But if I trace this down, that's like 1 point. Now you guys use your paper. Like, where do you think that?
Maybe 1.8 or 1.8.
Yeah, I'd say like
There was definitely a question mark on that.
1.79.
Yeah, 1.8.
1.79.
It looks like it might be. Yeah, it looks like.
And then where did we say 2 seconds is at?
93.
93. Sure. So this is 3 feet in 0.2 seconds approximately. So if we want feet per second, yeah, we're talking like 15 feet per second. Which if you've never heard FPS, often FPS is actually for frames per second with how quickly something's being recorded. So be careful. You'd probably want to use FTPS, or you can do FT/S. That's probably just as easy. It's about 15 feet per second. Now, interestingly enough, with data like this, I just read an article about how hurt will you get if a disc golf disc hits you in the head. Literally, they were doing the data of like how dangerous is this, and their models were exactly like this. Because think about it: when you throw a disc golf disc, when is it the fastest speed? Right when you release it, right? So if I hit you 20 feet away versus if I hit you 100 feet away,
If you make it 100
it's
feet away.
slowing.
Smack him with the disc.
can throw over 100 feet. Thank you very much.
I don't know, it might be really windy.
I can still throw over 100 feet. I'm pretty good, actually. You guys can pick on me if you want, but I'm pretty good. So we're at 15 feet per second. Now wait, then they asked 2.5 seconds. So at 2.5 seconds, what points did we use to approximate here?
Like 96.5? I don't know.
Yeah, I mean, this at 2.5 is pretty close.
Maybe 96.
Maybe 90. Sure, but I need another point.
Um,
Is that like on the up or on the down?
that looks like it's on the down.
It looks like it's on the down, so maybe if I use this point also, and that's at 95 feet, right?
But then it'd be like 2.7?
No,
Yeah, see, that's we'd have to estimate where that is.
It'd be very
2.7,
estimated.
2.65. Who knows? Approximately, what do you get there?
Oh.
You guys should have calculated these. I know it's easy to just sit and not do it because I make it easy that way. So if we have like 2.7 comma 95, and this was 2.5 comma 96, I guess. That's what, 1 foot per 2/10 of a second?
Yeah.
So what, 5 feet per second, I guess?
I mean, it didn't go much.
Now, what about that whole 0.1 thing? She's asking for 0.1 seconds.
I think it intercepts like at 5.
Well, where is the balloon at 0 seconds? 0 feet. So that's an easy
So
point to
0,
use.
0, and then I
So
thought
0, 0, and then
like
0.1.
5?
I don't know. Where does it look like on your
Looks like
paper?
it's about 5.
Do we agree it's about 5?
I want to feel like 4.
little less maybe.
I mean, well, look at your paper. I don't have it up here. It's on your paper.
I think it's 5.
I think it's 4.
So if it's 5, if we approximate the math.
Okay. Okay. Okay.
Hey, friends, we don't need to argue. If it's 5, what's your speed? Sorry. No, not 5 feet.
Oh, no, I'm sorry. 5 feet.
50 feet per second. 50 feet per second. Sorry, that's not SEC. And then 4 seconds, we were like way out here.
Oh, you can say that, of course, the beginning will have more speed because the parabola is steeper at the beginning.
Absolutely. So that's really the core of what we need to learn today, is that, of course, parabolas are going to be the fastest at the start and at the end, and they're going to slow down as they reach that apex point. Now, how does this relate to the equation? Time to overteach.
Every time
So,
you bounce that ball, I think of another parabola.
So Sasha uses her technology to know Al's balloon landed 4.5 seconds after it was launched. From the competition data, she knows Al's balloon reached a height of 81 feet. They've got cameras set up and everything. Like, think Mythbusters. So, here's the hard task. What's the equation of the function that represents Al's launch?
Equation of function. That's a lot of things.
Where is Al's balloon at the beginning?
Oh, well, we know the vertex.
0, 0.
Wait,
So-
we know a point of the vertex.
Okay, so start writing stuff down. So we know 0, 0. Write down 0, 0. We also know it ends at 4.5. Crap. 0, right? Our y is 0 again? Well, that's a fun function going nowhere.
And we know a point of the vertex, right?
We also know a point of the vertex. No, 2.25? I can't math today. I think, right? Because half of 4.5. 2.25, 81. Hey, what could we do
So that's one that's like
with
really
just
steep
these?
with it. You can find.
Find the
You know the x values or the x intercepts.
since I know my x-intercepts, this is x minus 0, or x plus 0. This is for my 0 of 4.5. So wait, from there I can build x squared minus 4.5x. That equals my y?
Yeah. So then you could solve for the y.
No, that's not my equation though.
No.
That's my equation just based off the zeros.
But you
We need another. We need a something.
Ah, the y. Ooh. Well, the y-intercept is 0. So we do have a plus 0, right? We do have the y-intercept here. That's fine. What do we do to test out if we have an A or not? Plug the vertex in, right? Plug in whatever other point we have. So if we plug in a y of 81, 2.25 squared minus 4.5.
Wait a minute, what? The 4.5
Sorry.
x.
Yeah, that should be replaced with 2.25.
Someone put that in their calculator.
Yeah, I don't think we're going to be anywhere close.
Magically, it comes out as a good number. That's a funny question.
I think we're gonna bet.
I just noticed.
Oh wait.
It's negative.
No.
81 equals like negative 5.
No, it's yeah, it's kind of negative.
81 equals negative 5, you guys. You can't change my mind.
That's a real bad.
Now wait,
lot of work
if
for
we're
us.
gonna say that there is an A somewhere, I hope you're doing this with me because this is why you guys end up struggling on the
A
mastery.
would have to be negative to make it positive, right?
It's like out here,
Yeah, it
right?
has to be negative because it opens down, right?
So we really, this is a result of this,
Yeah.
right? So couldn't we actually just say 81 equals A times x minus 4.5?
And then we could plug in the x.
Right, because that's just before we multiply out.
We could plug in the x's though, like.
We can plug in those 2.25s.
And then solve for a.
I hope you're practicing on your own.
2.25 and then because it's half of 4.5. Yeah. And then you do negative 2.25 times. Wait, yeah. 2.25.
Times 2.25. So what do you get?
A times negative 5.0625. And then you divide it by that number.
Yeah.
Oh, wait.
So 81.
So negative
Oh, what
something.
did I do? It's negative 16? No, maybe. Let me try that again. Or someone can check me because.
Yeah, I got negative 16.
Okay.
Wait a
Negative
second.
16.
Yeah, because it has to open down, so it should be.
Yeah.
Negative 16.
Yeah.
So if we bring that back up, and by back up I'm still going to move down, we'd have y equal to negative 16 x squared minus 4.5x.
I think so. What do you think? That's a really bad water balloon toss.
Wouldn't it be also multiplied by the?
Ooh, that's why I'm writing this and asking.
Yeah.
So wait, if this distributes in after this all, yeah, the A distributes into the whole thing, right? So my minus 4.5 is no longer minus 4.5. What is that times 16? Well, negative 16. 72?
Yeah.
So we think negative 16x squared plus 72x will model Jen's launch.
Wait, can you go up there?
Yeah.
Try it. Somebody with a graphing calculator, plug that in and let's see if we can find some of the points that we have.
I failed that. Oh, I need to do it. I need to do it in a window.
You want to know what this is?
How about?
Isn't that how much like the?
Why does this ball not stay where it is?
Because when it comes.
No, but why? Like, why? I'm putting it here. Why doesn't it stay there?
Gravity.
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 So
The A is the impact of gravity. Otherwise, we launch our water balloon and it like hits the space station, right? Like it just like keeps going. It can't. Something has to flip our parabola over and cause it to be parabolic. So this here, think about it, guys. Have you ever heard gravity discussed in negative 9.8 meters per second per second?
No.
Have you ever heard it as 9.8 meters per second squared?
I don't know what I do.
Gravity is speeding up, right? Gravity itself is constant. But what gravity does to you when you jump out of that plane is in the first second, it pulls you by negative 9.8 meters. In the next second, you already have some speed. So when it pulls on you, you speed up. And that's why it is multiplied by the time factor squared. So this is what we're diving in. Can I go up? You look this
wanted to see the beginning. Okay.
The beginning was use your zeros, build the factors. Then we plug in the other point that we know to figure out, is there an A? No, I still have a couple minutes. Let me check if there's anything else we wanted to talk about.
You know, Joshi, he told me this theory that if you knew the placement and every atom and the placement of every atom in the universe, then you could and you have an interaction.
So now that we have Al's equation, how does Charlemagne's equation change Al's? Yeah, I know.
What do you mean?
Hold on. So read this. Hey, read this situation. I still have like 2 minutes, and I'll still get you out of here early.
Oh, there's a contest. It'd still be the same because it's.
It's not the same.
No, wait. I thought you were talking about the parabola. It'd be the same. It just.
Well, it is the same parabola, but it's not the same parabola.
It is the same parabola, but it just starts up higher but it goes down low.
So what would the equation be?
It'd be the y-intercept would be 15 0.
So we would have negative 16x squared plus 72x plus 15. So before we get out of here, let me wrap this all up and put a bow on it. Gravity is actually 32 feet per second or 9.8 meters per second. But both of those per seconds are per second squared. So sometimes scientists will like say per second, and I think they're just sounding fancy. It's per second squared because when you divide by s twice, it ends up actually squaring that factor. But this is half of that, right? Negative 16 is half of the negative 32. So the other thing you'll probably see is negative 4.9 as an A value. That's your meters, right? That's half of 9.8. This, if this is gravity pulling down, and this is the location of where we started, what other thing is at play when I throw this ball?
Like the height you throw it at, or like
And the height that
where you throw it and how much speed you get at.
This has to relate to the initial velocity, right? The force I put on it. That's what the B value relates to. All right, with that, we can get out of here now.
Okay.
Have a wonderful day, guys. We're now talking about gravity and everything else, and it is awesome. You guys are super excited about gravity, right?
Predict the future. Like if you play everything out, like because you know every other atom in the universe, every
Yes.
No, I know the environment.